Welcome back to the Colloquium of the joint Heidelberg Colloquium, the first time with the Glühwein, you know. We're trying to make it an annual tradition, but we'll see how the speaker fares that has the Glühwein audience. But it is my pleasure to introduce Reinhard Genzel from the Max Planck Institute for Extraterrestrial Physics. He's the director there, and he started his career, his very illustrious career in Bonn, and then he went via the CFA to Berkeley, where he became a full professor, and then he came back to the Max Planck Society to head the institute in Munich. And of course, I'm sure everybody knows about his work about the galactic nuclei, and he will tell us a lot about star-forming disks, galaxies at the peak of galaxy formation epoch, and he promised he'll be entertaining with or without Glühwein. So welcome.
As long as I don't have to sing. All right, so this is a return to a very classic auditorium, very classic German lecture room, stern. You will be put to work. So I won't talk about the Galactic Center this time, but I will talk about what actually my group is doing most of the time, which is working on observations with new instrumentations of remote galaxies, and this field really has made a lot of progress. In fact, the whole field of galaxy evolution, of course, has made a lot of progress, and I'll show you what we found. So I'll start with this slide as an introduction for those of you who are not in the field, which basically shows the cosmic evolution of star formation as a function of redshift. So the early universe is here, that's where we are now. And over the last 15 years, it's become possible to construct this diagram and populate it with increasingly large samples of galaxy populations, which caused this evolution. Which basically says that there was a peak, a broad peak of cosmic star formation about 10 gigayears ago at redshifts between 1 and 2. And then as you go to higher redshift, the amplitude of that is going down some, although one has to take into account that, of course, time-space here is really rather compressed, so there's not that much time left between the Big Bang and point here, which is about 3 gigayears. And then, of course, a decay since that peak to the current epoch of star formation. So when you look at the galaxies which make up this peak here, it became obvious fairly early on from observations at sub-millimeter wavelengths that at least there is a fraction of the galaxies here which one would call in the local universe luminous infrared galaxies. These are objects which locally aren't seen, they're fairly rare. They make up about 3% of the cosmic local star formation rate and produce stars at a rate of about 10 solar masses per year and more. There are even a fraction of galaxies which we would call ULERGs in the local universe, so they would produce 100 solar masses per year. So for reference, the Milky Way does 1 or 2 solar masses per year. So these are very performing objects. And of course, when that was discovered, and with various surveys, more of the recent work, of course, has come from Spitzer, ISO, and then most recently the beautiful work from Herschel. It's been the question, what causes then this increase by a large factor of the volume density of these very luminous objects. At the same time, the Space Telescope, HST, has undertaken ever larger look-back surveys of the cosmological fields with ever larger coverage in wavelength space. And I've copied for you some of the more recent Candles images of some of the galaxies which you would find here. And you see, and that was clear to the early observers, they really do not look like, in the ultraviolet rest frame, which is what you're looking at, an opticon, do not look like normal galaxies in the local universe. So the picture everyone had about 10 years ago is that as you go about 10 gigayears back, you encounter a very large fraction of very luminous objects They look very different from the objects which we are used to as galaxies. So probably there are different physical processes happening here. So the one possibility everyone hit on was that they might be mergers and starbursts, because in fact in the local universe there's a lot of evidence that these lurgs, in particular U-lurgs, are dissipative mergers of gas-rich galaxies which happen to collide, and in this process of merging compress the interstellar media to an extent that they basically shoot up for a limited period of time and produce stars at a very high rate. So it was very natural to assume that this might be what's happening here at high redshift, and is causing this peak and the large fraction of luminous objects. So that's the state of affairs on the observational side, generally speaking, about 10, 5, 6 or so years ago. And what I'm going to tell you about this talk is that not all of this is rubbish, but much of it has to be corrected. Because actually many things which go into this peak are very similar, as you will see, to what we see in the local universe. It's just one variable has changed, and that's the fraction of gas. And so when you take that into account, take into account also what we are learning from cosmic accretion, from theoretical simulations, it now seems that much of what you see here can actually be explained, not all of it, but most of it, can be explained by the accretion of gas and minor mergers, not major mergers, in galaxies which grow and grow rapidly, and so they do naturally then produce very large star formation rates. So the field really is one where one is now going from integrated photometric observations to observations at ever higher angular resolution and coverage. We're beginning to cover variables other than the classical ones like stellar mass and star formation rate from optical UV tracers. And that's, of course, a technique which has been very much refined over the last 10 years. People generally believe you can measure measure stellar masses this way from population synthesis of photometric data sets to perhaps a factor of 2 or even better. Likewise, star formation rates, once you correct for extinction, which is an art, together with the simulations, which of course have given us a fairly sturdy and robust picture of the structure formation which underlies all of this. We can say something about the halos by basically comparing abundances of galaxies with the theoretical work. And then in the second row here you see all kinds of other new things which now is becoming available in spatially resolved fashion. Metallicity from direct optical tracers redshifted into the near-infrared, where increasingly powerful spectrometers are now allowing to get ever larger samples of galaxies. For the first time we are looking at the food for star formation directly, which is, as we believe, molecular gas and dust. We are beginning to also trace a very important quantity in the evolution of galaxies, which is not the gas which is coming in, but the gas which is going back out, which is essential, we know that from theory, to understand anything about galaxy evolution. We are also beginning to see the kinematics of these galaxies, measure whether they can rotate, or how much dispersion they have, etc. So we're really beginning to do in situ, spatially resolved, intragalactic observations of these galaxies in a way which I would compare to what was going on in a nearby universe in the extragalactic domain maybe 25, 30 years ago. And the powerful techniques of adaptive optics, space telescope of course, and interferometry with big interferometers is really currently leading to an explosion of that field. Maybe not as much of an explosion as in exoplanets, but still in the sense of how many people are working, it's rather impressive, and the progress which has been made. So in these studies, one thing which has become clear is that these galaxies which you see here at the peak actually live on a structure in the stellar mass, star formation rate plane, which is reasonably well defined. So when you go at different redshifts, so here's the local universe in Sloan, and increasingly large redshifts, as you see, too, in this peak regime, you can see sort of a sequence of galaxies which basically constitute most of that light. Not all of it, but most of it. I'll tell you how much actually numerically that is thought to be. And in this sequence, this main sequence of star formation rate, seems to have sort of the same slope, more or less. In first order, it's more or less linear with stellar mass, but the amplitude is changing with redshift, secularly. So basically, where a normal galaxies like the Milky Way would have 1, this redshift dependence goes like 1 plus z to the 2.8 power to at least redshift 2 or maybe 2.5. So this main sequence, which has a modest scatter of about 0.3 dex, plus minus 0.3 dex in the dispersion, is sort of where most of the high redshift star-forming galaxies live. So that was first recognition. Now, in studying these galaxies at other wavelengths, we are looking at different types of information. So the optical information, of course, here looks at the stellar emission, extincting, as I said, in various ways. But then if you want to study the gas, both in terms of the star-forming gas, like the classical optical emission lines, H-alpha, H-beta, nitrogen 2, O3, etc., or at the molecular lines, which you see here as a fence of rotational transitions of the carbon monoxide molecule, CO, which is for many studies the proxy to trace molecular hydrogen, which of course doesn't have a dipole moment and so cannot really be studied in any great detail, but the CO molecule can, and you will see that this has become quite a standard tool. And then lately, of course, one can actually study both emission of continua and also lines at the peak of any dust-enshrouded star formation. Of course, the idea here is in this spectrum, which is actually a nearby star-forming galaxy, that the energy initially is produced in the ultraviolet by stars. Then there's dust surrounding these stars, and they basically absorb most of the ultraviolet and then re-emit it as a quasi-gray body or black body, plus a host of spectral lines due to gases in the vicinity of these hot stars. So what we can do nowadays is go here in the near-infrared, which is the redshifted optical, with integral field spectroscopy. And that really has led to an explosion of new information. And all of the big telescopes are now equipped. We are very happy to have been associated in building this one here called Symphony on the VLT. And Symphony really has been, I would say, without being too bashful, the most successful of the integral field spectrometers on the big telescope. It is a device which basically takes an two-dimensional field, two-dimensional contiguous field, and then basically splits the light, like a normal spectrometer, dispersively, but then basically keeps both the spatial and the spectral information on a big detector so that it posts the reduction. You can basically, for each pixel on the sky, get a spectrum at the same time. So this kind of a spectrometer is very efficient, but also it allows itself to be very easily coupled to adaptive optics. Because of course you're looking at all the wavelengths and all the spatial points at the same time. When you then correct for the effects of the Earth atmosphere, you actually get very much improved imagery and spectral imagery with this kind of device. So we've been at it for now almost 10 years with Symphony and have assembled several surveys, which we now summarize here as the SIMS Z-Cosmos Symphony surveys. And this is slow going. Slow going, at any given time you get one galaxy. Okay, so while you have an imaging device, the field you're covering, even with a big detector, is actually fairly small, especially if you do adaptive optics. The field is about 2 or 3 arc seconds, so it's nothing you cover big fields with. You have to do one galaxy at a time, and the next galaxy, and the next galaxy. And at any given galaxy, if you want to get good enough information, you have to integrate for several hours. we integrate up to 20 hours per galaxy to get really best information, which I will show you here. By the way, that will be the same story for the millimeter interferometry. So for people who want to do Sloan-type surveys and believe that any number below 10,000 is equal to 0, don't have to stay here, because I cannot deliver that. It's just not possible. Nevertheless, the progress from 0 to 100 can be much larger than the progress from 100 to 10,000 sometimes. So this survey really has given us, at this point, a fairly good census of about 100 galaxies. Now the next big step in the field is just happening. We are also associated with this big machine, which is Symphony Squared. It's basically 24 IFU units patrolling a field of about 7 arc minutes. So you see, basically at any given time you can then actually pick up 24 galaxies, or more like 15 typically, because you also need to look at the sky. So about 15 galaxies per shot, and you integrate again in 5 to 10 hours, but now you have a multiplex advantage of a factor of 10. Unfortunately, not everything is glorious. This one does not have AO. ESO did not plan for that one. It should have, actually. But so at this point, any kind of a follow-up at high resolution, which I believe is very important, will have to go back down to one object at a time, and so that may not be the best. KMOS is incredible. The efficiency of KMOS, indeed, on the telescope is at least as good as Symphony. And in a week run we've had now, we already have assembled 200 galaxies. So it's just absolutely fantastic, the speed at which the machine is delivering excellent information. Now, on the other side here, it's the interferometry. Interferometry is a technique which most of you didn't know about, and certainly the optical astronomers studying galaxies wouldn't know how to spell, because basically who cares for molecules? But that has changed. Also the theoretical community, some are present here, are very well aware that of course the story of how the gas is coming in and is being used up in the star formation is an essential part of getting at a physical model of galaxy evolution. And CO emission is one way of doing this. It's not, as you will see, a perfect tool, but it is a reasonable tool for some of the applications. So we've used this machine here, which has 6 15-meter telescopes. It's a machine which is run by a collaboration of the Max Planck Society, the French CNS, and the Spanish IGN, and it's called IRAM. And this machine here is sitting at 2,600 meters in the Southern Alps, south of Grenoble, and was until sort of 2 years ago, the most powerful interferometer in the world. Of course, everyone knows ALMA does everything and is revolutionizing the world. It does. But if you apply, and I'm sure most of you have applied for ALMA time, your chances is 1/20 at this point, and there's only about 1,000 hours of telescope to go around in the entire world, so you are due for maybe an hour or two. We can take surveys here of most recent version is a survey we call FIBS2, which was just started, including some people here from Heidelberg, which will use up about 1,500 hours of telescopes as a major survey to really get at the molecular properties of the same population which we are studying here, which is studied by the HST community in molecules. And then finally, there has been, now it's a has-been, wonderful Herschel, where our institute again has been working very hard on one of the instruments called PAX. And PAX and SPIRE have made for the first time direct observations of these galaxies, these main sequence galaxies at high redshift at the peak of the emission. So here you get a colorimetric measurement of star formation rates. Now one has to be a little careful. You are limited, even with Herschel, how deep you can go, mainly because of the confusion with the extragalactic sky. And so you can only do the more massive systems, and the less massive system you have to use stacking techniques, and so there's a certain limitation of what Herschel has achieved, but what it has done is for the first time really give us a census of how much emission comes out, what the calorimetric star formations are, and in a way to calibrate the extinction-corrected star formation rates which you can get from all other surveys to a much better degree than has been possible. So that's the kind of work we're being engaged in. The way we work at MPE is, as you see, we build instruments, but we also try to take the information from different wavelength range and really bring it together to see whether we can learn things. Let me try to summarize things in various areas of these high redshift objects which we are beginning to understand more and more. The first question, of course, you would like to know how much really of that cosmic star formation rate is associated with this main sequence, and how large, what fraction of objects actually happens away from that line. That's important because objects which are way above the line, you would expect, well, these are really objects which are not normal. They are probably short-lived. They're probably starburst objects. And so here, from a paper by Rodigiero, is a cut perpendicular to the main sequence, up and down, integrated over mass, of the specific star formation rate volume density. And you can see basically that log normal distribution here, that's the main sequence, and then that you would call the outliers. So in that sense, you can quantify that at all redshifts actually, about 10% of the cosmic star formation rate, or 5% in numbers, is actually in this outlier component. So it seems now fairly safe that the earlier interpretation that this peak of cosmic star formation rate was due to short-lived starbursts is actually not correct. Unfortunately, not many people, or not all people in the community have taken that in yet. They still hang on the words ULERGs, and basically, because something is luminous, interpreted in the sense of star formation rates which are well understood to be merger-driven starbursts at low redshift. But that story does not seem to be correct at high redshifts. Other information, basically comparing correlation functions or looking at the fraction of blue and red objects, and also the circular velocities, indicate that the duty cycle of these objects on the main sequence is reasonably high. The number is, as you see, quite uncertain, but so 50% of the time they live on this main sequence. And so indeed, these are not starbursts, but seem to be more equilibrium objects. So what is the physical meaning of that main sequence? Let's look first at the lower diagram here, which is from a paper by Stein-Voits in our group, who's used HST images in 3 redshift slices. So these are hundreds of thousands of galaxies involved here. And basically for each galaxy, he would derive from the light distribution the Sursage index. And the color scale here is that black is n equals 1, Sursage index equals 1. So that's what you would derive for an exponential distribution, and generally people would expect that this is a disk-like galaxy. While the redder color galaxies are more cuspy objects, so here the very red is n equals 4, so that would be a Devocoleur object, which really has a very peaky distribution, which you would associate with, say, elliptical galaxies or other dissipative systems. And you can see that at all redshifts, the main sequence, which is this white line here, along the main sequence, is basically the locus of where n equals roughly 1. So indeed, from a structural point of view, the main sequence in star formation also is a structure in galaxy structure, and appears to be where the exponential distributions lie. The next part of the story comes from the kinematics, which we've been looking at with Symphony. And I'll show you now that this indeed is also true when you look at the kinematics. These things are disks in the sense that they're rotationally supported. And so Let's look at that. So what you see here is a bunch of velocity fields in H alpha of about 40 or so of these SINS galaxies, and they are ordered in a way where, as you go here, the upper left corner, the velocity fields are fairly regular. So basically, as you go from one side of the galaxy to the other, you see the velocities change from blue to redshifted velocities. You can also see the amplitudes here. So here, in this galaxy, that would be plus minus 180 kilometers per second. All of these objects are on the same scale. So these are the big ones, and these are the small ones. And then you can see down here, in this regime, the velocity fields are fairly irregular. So that's what you would sort of naively, qualitatively interpret as objects which might be mergers. So these objects, you know, from most people who've seen a rotating disk galaxy would say, hey, that looks pretty much like a disk. Now, of course, the way this goes is initially we had one object, or two, or three. And most people in the field, even including Hans Walter, would say, that's anecdotal evidence. But actually, over the years... Well, you were just looking at me, honestly. And you have a good blue mind, so you can... So of course, you know, how would you prove to people in your community that this is actually rotation, while some of the other things are not? Well, you have to be quantitative about it. You also would like to have a higher angular resolution. These data here are all at seeing limited resolution. Seeing limited, so it's about half an arc second. That's pretty good, but that's not good enough, turns out, to really resolve some of the more cruddy and smaller objects here. So in fact, one of the jobs we had to do in the SINS program is to replace that set of galaxies by that set of galaxies, which is when you now basically go at each and every one of these systems and spend 5 to 20 hours with adaptive optics, laser guide style adaptive optics, and basically get much sharper images and of course much higher resolution, higher quality spectrum. So it's very clear that in these galaxies up here, they exhibit what people in the kinematics regime would call spider diagrams. If you want to demonstrate to somebody that you have a rotating galaxy, what you want to see is, of course, that one side of the galaxy is blue and the other one is red. But that's not sufficient. That's only necessary. You actually want to see also that if you don't resolve the galaxy, that the velocity dispersion, which you get from fitting to each pixel, the Gaussian, is a maximum in the center, because that's where the galaxy, which is blue on one side and the other side, of course, because you don't have high enough resolution, smears the rotational amplitudes to basically a large dispersion. Next, if that galaxy has a stellar emission and there is a bulge, you want to expect perhaps that there is a bulge in the center. But actually for these galaxies, at least in the ultraviolet light, that does not seem to be the case. We come back to that, however, with optical light from candles, and there it does indeed appear to be possible. The next one is that the velocity change is not only, of course, along the major axis, but also perpendicular to the major axis, in ways which you can predict, given the inclination of the system. That's called spider diagrams. So isovelocity contours are curved and so forth. So that is how you would quantitatively establish that. And in fact, in our group that was looked at by Christian Shapiro, who developed a technique called kinematry, where you would take a galaxy velocity field and velocity dispersion field and basically do a Fourier transform of the velocity along a circumference of the galaxy, and then basically analyze the power in the different Fourier components. And then if it's a rotating system, you would see only the low components, and if it's a more complicated velocity field, of course, you see higher components. So if you do that, you can show that indeed all of these systems up here are very, very likely rotating disk galaxies. You can also see that many of the systems over here are not. Here, in fact, the velocity dispersion is still large, even if you have high resolution. Not for all of them. I mean, this one obviously has a nice velocity gradient, this one has too, but here are some systems where there is not much regularity. So there is a class of galaxies which have become to be called dispersion dominated. Well, elliptical galaxies are dispersion dominated. But this is gas. Elliptical galaxies can be dispersion dominant in the sense of pressure, basically upholding gravity because you have stars which don't collide. But gas dissipates by collisions, of course, very rapidly. So to make a gas dispersion dominated galaxy is something which really is quite not intuitive. That seems to be a new kind of galaxy. And then, of course, there's a fraction of mergers. So when Kristen did this analysis, initially out of a fairly limited sample, the number she came up with is at least half of the bigger systems, because that's what was required technically to do the work. Half of the bigger systems or so are disks. The other half look either to be dispersion dominated or mergers. Certainly the major mergers are a minority of this class. Other people in the meantime have taken up the same kind of work. There are several groups in the world doing this with different instruments on the Keck, on Gemini, etc. And they find pretty much the same thing. And the better the data are, higher resolution, even in lens studies, the fraction is even maybe higher. So I would say for those galaxies where we have good enough data nowadays, one would say probably 2/3 or maybe as much as 3/4 seem to be disk-like rotating structures, although as you will see, very different from the local disks in terms of their underlying velocity dispersion. And then some fraction are smaller systems which look like dispersion dominated, although in a fraction of those that may be a reflection of the size and our incomplete resolution. There may still be disks. So we've learned that there is a good fraction of these disk-like galaxies. So now we come to this issue of dispersion. So of course our Milky Way has dispersion in the interstellar medium, about 5 to 10 kilometers per second on large scales without actually much of a change. You go anywhere in the Milky Way, you see about the same amount, unless you go into the center of the Milky Way. If you forget about the center, in the disk of the Milky Way, it's about 5 to 10 kilometers per second. So the ratio of the rotation to this distributed floor of dispersion in local disk galaxies is about 10 to 20. So that gives you a feeling for the aspect ratio, the thinness of the modern disks. Not so for these high redshift systems. Here's from most recent paper by Natasha, in fact, a plot for each pixel for a bunch of systems. So we measured for each pixel the velocity dispersion. Now there's a lot of uncertainty here, as you see from this graph, but basically what you should see is a scatter diagram. A scatter diagram basically showing that there's not much of a dependence in this case on star formation surface density. The reason this was plotted against star formation surface density is, of course, one of the possible ways to make a galaxy highly turbulent is to inject a lot of energy from stars. And since the star formation rates are so high, if feedback from stars is an origin of this high star formation, this high turbulent velocities, might want to see whether there is a correlation. Now it turns out that work by Shetty and Ostreich and others have shown theoretically that this may actually not be necessarily what you would expect theoretically. But the main point I want to make here is that the average value in all these objects, wherever you look, is still about 60 kilometers per second. The rotation velocities in these bigger systems, again, are like in the Milky Way, about 200, 220 kilometers per second. So V over sigma now is not 10 to 20, but say 3 to 5. So you have to think of these early disks as very puffed up, irregular objects. Very puffed up objects with a lot of dispersion. Now this cosmic dispersion seems to indeed regularly and secularly change with redshift. We're beginning to explore this, and our KMOS 3D survey undergoing will flesh this out in some detail. So this is from a number of sources in the literature, which you can all see listed down below. And there's a tendency that indeed this velocity, this galactic velocity dispersion decreases from high values at high redshift to ever lower values at low redshift. So clearly you can see these disks settling down over cosmic time for a number of reasons. Now we do not know, and it's not known in the Milky Way, what drives the dispersion. We have experts sitting here in our various options. I already talked about feedback. Another option here at high redshift, we'll come back to this, is the instabilities in these disks, basically creating inhomogeneities in density, which are interacting through gravity and basically lead to torques in the disk, which puff up the velocity dispersion. And it could be also that the gas, which is accreting from large distances from the intergalactic web into these disks, is injecting enough gravitational energy to increase the dispersion. So all of this is possible. There have been on the order of 10 to 12 theoretical papers written over the last 2 years on this subject, and they all disagree with each other. So I'm fairly sure we don't know the answer at this point. But the principal points are pretty obvious what might be driving this. Well, let me come to the molecules. So, as is practiced in the local universe, what high redshift you do is you observe this galaxy at high redshift in a CO transition. Because of the redshift, we cannot use the lowest CO transition, but typically use 2 to 1 or 3 to 2. You don't want to go too high because then you expose yourself to issues of excitation. So you want to go to a line which is observable in one of the lower millimeter bands, but then you don't want to go too high because then you don't know how to convert this signal into molecular gas. And then basically what is done is to take the CO line luminosity and multiply it by a fudge factor, and then you call that the molecular gas. Of course, most of you who have not done this might think, oh, okay, there must be somehow the abundance in there, and so forth. And that is actually not the case. This conversion factor is a fairly complicated function, how to convert an optically thick line, it turns out, into a molecular gas, and it's certainly introducing an uncertainty of factor of 2 or so. But when you do this, you find that the molecular gas fractions at high redshift are fairly high. About 5 to 6, 7 times higher than the local universe. So the Milky Way has about 7% and 8% gas fraction. So these high redshift galaxies are very rich in molecular gas, about 30 to 50%. And in fact, there is a strong correlation, as you see here, both for the local universe, which are the red points, and the high redshift points, between this molecular mass, gas mass, relative to the stellar mass, and the specific star formation rate. So what that tells you is that as you go at some redshift, you go up and down in the main sequence, up and down. You're basically going from low to high gas fraction. So the primary variable in this thickness of the main sequence is gas fraction, it appears. And then we go from low to high redshift. You can see that these gas fractions are beginning to regularly go from low values, which here is sampled from the cold gas survey of Guinevere Kaufmann and Amélie Saintonge to the higher redshifts. And we don't know what's happening beyond, and maybe actually some leveling off, but you can see this really seems to be a trend, a secular trend, like with the velocity dispersions. This is unlike the H1. We have, of course, no direct 21 centimeter observations of high redshift systems, but extrapolating from the Lyman alpha absorption line measurements, one would say in H1 this seems to be a rather flattish distribution. So the low redshift universe, the cold gas in galaxies is dominated by H1, not molecules. The star formation is, but not the overall gas content. At high redshift, galaxies are molecular dominated. So you're telling me 10 minutes, huh?
No, it's less than that.
Less than that. Okay, all right, well, start singing. Right. Okay, our theoretical concept. Of course, I'm ashamed, Volker sits here in the audience, to give you a very simplified way of how we might now look at this. And this is really one which is very much motivated by the fact that we want to connect the direct observations of all these numbers we have to some measurable quantities from the observation in an empirical way, rather than having to rely on detailed simulations, although we do that too. And that, in fact, has become to be called the bathtub model. It's a shame in many ways, but it describes the essentials of what these equilibrium systems are doing. Gas is flowing into the galaxy, is leading there to a gas reservoir. Stars are forming out of this reservoir. Stars are ejecting gas back out of the galaxy through supernovae and radiation pressure and stellar winds, etc. So you have a constant in and outflow out of these galaxies, and you can look at this all in terms of a continuity equation, where this accretion, of course, is dominated in terms of the modeling by the structure formation. Then you have the star formation rates, and then you have some recipe for the outflow rates, which here are termed in terms of a mass loading factor. So we want to determine this mass loading, we want to determine the rate at which galaxies deplete their gas reservoirs and how quickly they can do this, etc. One tool to do this is the so-called Kennigan-Schmidt relation, where you plot the molecular gas versus the star formation rate, and you basically measure the ratio of the two. First off, I should say that like in the local universe, which Frank Biegel, Leroy, Fabian Walter and others have looked at, there's a more or less linear relationship in these blue points. Linear relationship means that there is a characteristic time scale over which these galaxies empty their gas reservoir if they don't receive no gas. And that time scale in the local universe is about a gigayear or two, and so it is at high redshift. And this number, this half a gigayear to 2 gigayears, is significantly less than the Hubble time at all these redshifts. So one of the immediate conclusions is, unless these galaxies get fresh gas, they won't stay on the main sequence. Okay, they won't stay on the main sequence, and so they have to be replenished more or less all the time, semi-continuously with fresh gas. That is an indirect, but a fairly powerful argument in favor of what we all believe, which is that gas is coming in from the halo and filling the gas reservoirs. This depletion timescale, I should say, seems to be a fairly slow variable of time. And so really the main thing which is happening here is that the accretion rates drive the gas fractions of galaxies. So here's a picture of one of these galaxies, and I want to end with a hopefully short description of how we understand these irregular systems. These systems which do not look like normal galaxies, but I told you, these are disk galaxies. Why do they have such big clumps of star formation? And the answer is probably that in a high gas-rich environment, the gravitational instability really creates very large scales, which are gravitationally unstable. That's the Toomer length. And the Toomer length is proportional to the size of the system and the gas fraction. And the Toomer mass of that length is square to that. So while in the local universe, the biggest structures are a few hundred parsecs, and 10 to the 7 solar masses, they're huge in the high redshift universe because the gas fractions are huge. And so that really means that these high redshift galaxies are like normal galaxies in the local universe in many ways, but the large gas fractions lead to high velocity dispersions if Q is about 1, and they lead to these huge star-forming complexes, which is at the largest unstable scale. Now, as to the outflows. The outflows, of course, in these systems have been seen for some time through absorption in the ultraviolet. We are now beginning to see them within these galaxies in emission through H-alpha, and hopefully soon in molecules. They show up as broad components here, and we can trace in several systems these outflows to the individual star-forming knots, okay? So we can actually prove what everyone would accept as a fairly reasonable assumption, which is that these outflows are driven locally from these star-forming systems. We can show that these outflows have sort of a threshold in star formation surface density, below which these galaxies do not drive local winds, but above they do. That's like in the local universe. There's also a threshold of about 0.1 solar masses per year per kiloparsec. But in the high redshift universe, that threshold is much larger because the gas fractions are larger. When the gas fractions are larger, that means the pressure of the interstellar medium is higher before you can have a breakout of these winds. With the molecules, we're not quite there yet, but pretty soon, I'm sure, we can look for wings and look for these outflows. Finally then, how do these systems evolve? Because these star-forming clumps are so large, their friction is large. Basically, viscous effects and dynamical friction goes like V over sigma squared, or gas fraction squared, times the dynamical timescale. So in a modern galaxy with low gas fractions, that number here is very, very large. So basically they evolve on gigayear timescales. In the high redshift universe, on the other hand, large gas fraction means V over sigma is large, these clumps are very large, and that means the friction is large. Basically, the frictional scale lengths are large. And so we're talking about viscous timescales which are only a few times the dynamical timescale, and all of the simulations which have been done predict that as long as these clumps here do not blow themselves apart by star formation, they will inspiral and form bulges. And we see that actually. You see, I am behind time, and so I better go to this. So I've shown you this before. These are these H alpha velocity fields, and from low mass to high mass. And so then when we go to the high mass end, nice part of the talk, which we need is go to the high mass end. In stellar distribution, we see that indeed these big disks in stellar distribution have big bulges. Okay, so in fact, the tenet now is becoming that there may very well be a second channel of producing bulges in addition to the major mergers, which is happening in many of these systems very plausibly because of this high gas fractions leading to very fast inflow timescales in these disks. Well, I had some things to say about quenching, but it's more important that we have our blue line. Okay, thank you.
Thank you very much. Thanks for being on time. And so I think there's a lot of questions on the beautiful part of the talk that we did get to. As always, students first. Is there any questions from the students on this? Hans Walter is not a student. Not most students. Okay, postdocs included in the first round.
Oh, God.
Go ahead.
I have a question about the definition of the main sequence. How do you select the galaxies when you define the main sequence?
Oh, there are various ways, and they all lead more or less to the same result. So the classical way is you make a magnitude-limited survey in the Hirsch frame ultraviolet or in the optical. Then you make a color cut, which, based on models, would get you to that kind of a redshift for typical star-forming galaxies. Then you get a subsample of that, and then finally you do spectroscopic follow-up of this. Now this general technique you can do in various ways. You can find the words BX, or line and break galaxies, and BZKs, and so forth. So various ways of choosing the colors which you select, and therefore also have some biases. I mean, if you pick it all in ultraviolet, you tend to get bluer systems and so forth. You can also go ahead and make the selection based on K-band images. You can do it from Spitzer mid-infrared emission and then go back through the whole system. And then finally you can do it at the very longest wavelengths with objects which radiate strong sun millimeter emission. So there are various techniques which you then have to cross-calibrate. And in fact, that's where Herschel comes in. Basically, we have now very good cross-calibrations. Now, I want to get trustworthy enough that we are fairly sure we're not missing too much, although clearly the ultraviolet samples, which are most numerous, tend to pick mostly the not-so-dusty objects, that's for sure. Yeah.
So just so on the, if you look at the distribution as a function of specific star formation, on the low side of the specific star formation rate, there's a drop in the main sequence. So is that a selection effect, or is that a real drop?
No, that's so to speak. I mean, and if you go further, you'll then get into the red sequence, right?
Yeah.
Now, in terms of amplitude, the blue sequence is like this, and then the red sequence is a little broader distribution. But there is sort of a minimum, or at least a sort of significant drop in the population there. Yeah.
Can also use gamma reverse to replace star formation rates. Make that consistent result.
The question is, what about the comparison of these kinds of selections, I'm paraphrasing this a little bit, these kind of selections to ones based on gamma ray burst samples. Now, gamma ray burst samples are indeed right now in the limit of 100 objects, and so what we're confronted with at this point is a potential difference in the Madal plot, which I showed, where you see maybe the gamma ray bursts are perhaps falling off less rapidly and so forth. I'm not sure, or are you sure that this is yet believable? I think I would not personally believe that the gamma ray burst populations are useful in the sense of understanding cosmic star formation rate. I think they are like what we're doing, more another way of looking at it, which is gamma ray bursts take a specific physical process within these galaxies, and let's understand what they are. Low metallicity regions, obviously, peak more toward the brightest star forming sites and so forth.
Sharon?
So you showed us that there's virtually no correlation between the gas velocity dispersion and the star formation rate. But I was wondering if there could be expected to be something between the velocity dispersion and the specific star formation rate, which would take into account the depth of the potential well or something like that. No, nothing.
No,
That's surprising. Because
I mean, of course, this is, let me say, technically, I've glanced, as you of course see, since I had so much material, too much material, I glanced over all the technical work. If you look up in the literature there, you will find some papers which find various correlations. I would say these are all bogus correlations having to do with the fact that you're going at this, at best, with 6 to 8 linear resolution elements across the galaxy. You have to first remove the rotational signal. Many people don't do that, and then you get all kinds of crap. Okay, so what I've shown you here is indeed the best we can do, and so in a few galaxies we have enough resolution to then actually look across a clump and see whether they're, and so far absolutely no correlation with anything. It's just a flat scatter plot, so to speak. There may be things which we cannot say because we just don't yet have good enough data, but at the level of 10-20 kilometers per second variation, there's nothing.
But given that you expect that the higher gas fraction systems have the higher line widths, and gas fraction, let's say, is something like specific star formation rate, if you believe that the molecular gas is tracing the star formation, then wouldn't you expect something?
Absolutely not. A very good point. That's a sub point. So in fact, I could have shown you a plot of loss dispersion versus galaxy size. And so you go to the small sizes, that's where these dispersion-dominated galaxies live. And what you would learn there is that sigma is about constant, more or less. V, which is the rotation velocity, goes down. So V over sigma for the dispersion-dominated galaxies goes down. That's why they then are called dispersion-dominated. Yet their gas fractions are high. So there you have that effect.
Angela?
Yes, the sizes you show for the clouds, I mean, how resolved they are. I mean, you get the symphony data.
Yeah, so with Symphony, which gives you typically a resolution of 1.6 to 2 kiloparsecs, you're beginning to resolve the big clumps, but not the small ones.
So okay, even these big clumps, if hypothetically you can have an infinite resolution,
yes,
there will be
substructures.
I will think of myself of giant H2 regions.
Absolutely. Understand the theory behind it is in a rotating galaxy, The Turner instability is the largest unstable scale. But everything below the Turner scale, down to the Jeans scale, is unstable. So if you picture these pictures, think of the antenna galaxy. Yeah? All of these big things, we have smaller things and still smaller things, but there are also big things. So for instance, the scale of a globular cluster. So one of the possibilities here is there are, within these big structures, maybe gravitationally bound globular cluster scales, which might form. And they might actually then be left over after all these things get destroyed. So, but don't think of this as only one blob. Absolutely not. And there cannot be, there stars in there, right? So they're infinitely small. Yes.
You have the interesting term of morphological quenching on that slide there. If I recall that correctly, then it says that the gas stays in the system, but it cannot cool and clump anymore because of the velocity dispersion of the system.
Yeah.
And now I'm just curious whether you have real evidence here in several cases.
Right, so thank you for allowing me one more slide. So quenching is a big issue here, right? And so we are trying to go hard right now after the physical evidence for quenching. One thing I would have shown is we are beginning to have the first evidence for nuclear outflows, okay, in the most massive systems. This evidence here is basically showing that more than half of the systems we have show H-alpha rings. And so that means there is less or no star formation in the bigger systems in the center, while fairly powerful on the outside. At the same time, the dynamical modeling can be combined with Kennicat-Schmidt to give these plots over there, which are radial plots of Q. So Q is less than 1 in the ring region, so that's where the global instability happens. But you see, they're upsloping. And in the more massive systems, which are the red ones, it's upsloping a lot. So Q is much greater than Q critical. So this is potential evidence, I would say, interesting first evidence that indeed this could become stable first in the inner regions. Then you get sterile gas, and then the question is what happens to it? If the gas is sterile, it would hang around maybe, and you get more gas, you would think, and then it goes up in star formation again. Or it could be driven out by outflows. Or actually, this may lead, and that's what the models are beginning to show, to a interrupt of the conveyor belt into the center of the galaxy. Okay.
So I was wondering about the hidden mass dependence of your mass loading factors of your outflows. And better, first of all, what do you find? And does it constrain any of the model from the driving?
Yeah, no, I mean, so in H-alpha, so this is, ionized gas, in the low temperature ionized gas component, we are finding plausible numbers of mass loadings of 1 to 2, 3, sometimes even 8 in the most extreme clumps. But galaxy-wide, 1 to 2. That's sort of the numbers which the best feedback simulations are beginning to show. Now, A, we're not tracing the hot stuff. So multiply by 1 plus the hot fraction. We are not tracing the molecular gas yet, although, as I said, this will come pretty soon. And so I would argue that what we are getting is a lower limit. Now, if the lower limit is strong, like in M82, you would have to say the ionized gas, the H-alpha, is a small fraction of the total outflow. The outflow is all more or less in the hot stuff. Yeah? If that is the case, well, we're really in trouble. Okay, so, obviously we would like to know what the hot fraction is in the outflows, but that is going to be very, very difficult. The molecular stuff we will get, and that of course will be very interesting in terms of really seeing how much of the overall galaxy is blown out, or at least driven out, taken on.
How does it depend on halo mass or stellar mass?
I would not. I mean, at this point, technically, I'm proud to say that we're just about, for a stack of about 8 galaxies, can remove the emission measure part of the, this is technical again. H-alpha is great, you don't have an abundance to worry about, it's optically thin, okay? We know the sizes, so we can actually, you can divide by a size. And And it's hydrogen, yeah, okay, so we don't have an abundance. But we have one more rate, which is density dependent, right? Because emission measure is proportional to n squared. So we would like to have the local volume density, and that we can get through the sulfur line doublet, right? And so we are plausibly beginning to have good enough signal noise ratio to measure the doublet ratio in the broad line. And that gives you these. That's hard stuff, okay? ELTs would be highly welcome for this kind of work.
Okay, open to everyone. Humble.
I'd love to move you one slide forward, but can you go one back where you talked about the bulge formation?
Yes.
So people had talked about what they call secular bulge formation, where bulges form by making very massive thin disks and in simulations they couple and form a bulge.
Yes.
Do you have any sense of whether your observations point in that direction, or whether it's still true that in the inner parts, simply gas forms a vertically hot population of stars to begin with?
Yeah, so in the paper, this on AstroPH, the paper, first of all, we're talking about some fraction of the early bulges, right? I don't know what happens to redshift 0. I'm completely ignorant of this. So we are looking at the possibility at high redshift, there's a channel due to this inflow of gas. And so then hopefully I have the slide somewhere, otherwise I'll describe it, or otherwise you look it up on AstroPH. We constrain, of course, the amount of material in the nucleus from the dynamical modeling. Then we have the Genzel's stellar mass there, and we have the molecular mass to the extent we can extract it from H alpha. Very dangerous, because we have no spatially variable extinction. We have it not in our hands. They'll come with armor. So we can compare the dynamical mass in the nucleus versus the two others. And it appears in the more massive systems, the stars are taking over. So that is, that is consistent with the buildup of the bulge, while in the lower mass systems, it's the gas. So I would say what's happening is gas is streaming in, but forming stars. And then over time, we build the bulge. And then the whole thing is shut down, perhaps, by various processes which we've talked about. So unfortunately, I think to me this is a sellable physics problem. I mean, it's not going to be one thing. It's going to be a complicated interplay of different processes. We haven't talked about the halo part of it.
Could you also imagine the scenario where you can have bulgeless disks? So the clumps do not go to the center. Is that a possibility?
Well, I mean, we do see these bulges forming. I cannot deny that I'm quite happy that a fraction of them have had major mergers, okay? So I'm not against major mergers at all. But I would say, given merger rates and so forth, it's unlikely that all these bulges form that way, so that's one way of forming. The simulations which have been made feel or seem to indicate that it doesn't really matter whether the big clumps survive as a unit going inwards, or whether they semi-self-destruct by feedback, but generally still drag much of the gas, and also stars along and gas comes on top of it. So as long as the conveyor belt goes, and the conveyor belt requires large gas fractions, that's really what it is. So you get these long scales of friction. Anything is sort of dragged with it, stars, gas, and so forth. Efficiencies, I'm not sure one can trust the simulations at this point to really know what the answer would be.
I'm wondering whether at these high redshifts we can say anything about the INF of this stuff on the galaxies. Is there a way to constrain it? Maybe by comparison with space galaxies?
Yeah, we tried that by comparing dynamical masses and then against some of stellar and molecular masses. Well, not good enough. Not good enough, yeah. I mean, first of all, there's dark matter. Okay, so what you find, I can give you the technical answer. The technical answer, averaging over the best galaxies we have, you get a baryon fraction of 80%, so not much dark matter, and this is for a short radium IMF. But am I really sure? It's a tricky thing to measure. I mean, after all, you're talking about what, 50% effects. To go to 50% effects with all these systematic error bars, which are each maybe a factor of 2, I'm just not comfortable. But I mean, I think, I would say, I just heard it, saw Schechter's talk on sort of his way through lensing of confirming, I guess, the low redshift elliptical bottom heavy IMF. I mean, that seemed, from all I know, the best I've seen.
Do you have any other questions? Again, and I think with that,
Thank you.
actually, one question. Do you still have some blue light or no?
I think it's now kicked off. So
Okay.
let's keep